Here we go with some simulation. It's the imitation of chance behavior based on a model that accurately reflects the simulation. So we're modeling what's going on without actually doing it. So we're going to look at a few different examples here, and we're going to look at how we can design simulations and carry out those simulations. And to do it, we are going to use our four-step process. We first state. We want to make sure we understand and write down what the question of interest really is. We then make a plan and we write this plan out in a way that somebody could just pick up our plan and do it without knowing anything else. We should be able to hand this to anybody and have that person carry out our plan. And this is the do part. We're going to perform many repetitions of our simulation, and then we conclude. We use the results of our simulation to answer our question. So we're looping back around to what we stated in the beginning. And we can use physical devices such as dice, cards, spinners, coins, or we could use random numbers such as table D, or even a random number generator, which we'll look at how to do in our graphing calculator to do these simulations. So, golden ticket parking lottery. Before we get into this one, let's look at some different state plan do concludes. So here are three different scenarios, three different questions that we're looking at. And these are just examples of what we would state, plan, do, and conclude, what these sorts of things should look like. So take some time, look at these three scenarios, and if you have questions, make sure that you're asking. But here's our golden ticket problem. We have a high school, 95 students, permission to park on campus. Each month, the student council draws 2 names that are given reserved parking spots next to the main entrance. Last month, the student council member from the AP Stats class drew the names. And both golden ticket winners came from that class. And because of that, because the 2 winners came from the same class that the drawing person was in, some people thought it was rigged. There are 28 students in the AP Stats class, all of whom are eligible to park. Design and carry out a simulation to decide whether it's plausible that the lottery was carried out fairly. So state. What's the probability that a fair lottery would result in 2 winners from the same AP Stats class? Here's a plan that we could use. Use Table D to simulate choosing the golden ticket lottery winners. Since there are 95 eligible students, label the students in the AP Stats class from 0 to 28, and the remaining students from 29 to 95. Numbers from 96 to 00 will be skipped. Moving left to right across the row, we'll look at pairs of digits until we come across 2 different labels from 01 to 95. The 2 students with these labels will win the prime parking spaces. We'll record whether both winners are members of the AP Stat class. Just a yes or a no. So let's look at this actually carried out. So here's our labels. We're going to start with row 139 in Table D. And we should change this up as we do different experiments. We don't always want to start with row 1. So we're starting with row 139. Look at pairs of digits. So here we are. That row starts out 5558. Those people are not in the AP Stat class. The next row is person 89 and 94. Those aren't in there. Person 4 and person 70. The first person is an AP Stat. The second person is not an AP Stat, so we say no. The next pair, neither one is from AP Stat, so we say no. The next pair, we have 10. They're in AP Stats. 98 would get skipped. 43 is not an AP Stat, so we say no, and we continue going like this. And if we keep going, we'll see there's one that matches our both from AP Stats. Nope, nope, no, 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 yes, no, yes, and we continue going like this. Looking at 18 repetitions, both winners came from the AP Stat class 3 times, so the probability of this happening would be 16.67%. 3 divided by 18. Another example, page 291 in our AP Stat book, but here is the problem written out, the example. So, breakfast cereal, NASCAR promotion. Each box of cereal will contain a collectible card. I used to love these cereals when I was young. Not necessarily NASCAR, but I loved getting stuff in my cereal box. We have 5 NASCAR drivers: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, and Jimmie Johnson. The company says that each of the 5 cards is equally likely to appear. A NASCAR fan decides to keep buying boxes of cereal until she has all 5 drivers' cards. She is surprised when it takes her 23 boxes to get a full set. Should she be surprised? So, state. What's the probability that it would take 23 or more boxes to get a full set of 5 NASCAR collectible cards? We're going to use random numbers. We're going to use the calculator to generate these. We need 5 numbers to represent the 5 cards. 1 is Jeff Gordon, 2 is Dale Earnhardt, 3 Tony Stewart, 4 Danica Patrick, and 5 Jimmie Johnson. We'll use the command ranint 1, 5 to simulate buying 1 box of cereal and looking at what card is inside. But one thing to note here is since we want a full set of cards, we keep pressing enter until we see the labels 1 to 5. It's okay if the numbers are repeated themselves. What that means in this problem is that we just have 2 Dale Earnhardt Jr.'s, or if we get a run of 5 3s, that means we have 5 Tony Stewart cards. So first off, let's jump to our calculator. Let's make sure we know where to go. Menu, probability, random, and we want random integer. I'm just going to do 1, 5, and I push enter. There's my first random digit. So this means I got 2 of the 5s. I got 2 Jimmie Johnsons and a Jeff Gordon so far. And Tony Stewart. And another Tony Stewart. And a Danica Patrick. And another Jeff Gordon. And a Dale Earnhardt. So now I've gotten all 5 cards. So, if we did this a whole bunch of times, we did it the first time. Here's an example where it takes 9 boxes. Here's one where it takes 15. Here's one where it takes 10. And if we do this over and over and over again, we see this sort of distribution if we make a box plot. It's not a box plot, what am I thinking? This is a dot plot. You guys knew that. Good thing you're paying attention and I'm not. But here's our dot plot. So should it take 23 boxes? Well, no, based on our simulation, it never takes us more than 22 boxes to get a full set of cards in 50 repetitions. Our estimate of the probability that it takes 23 or more boxes to get a full set is roughly 0. So, is that bad? Did the company maybe not do a good job of advertising? Yeah, it's very possible. So there's 2 simulations designed and carried out, one using Table D, one using a calculator for random numbers. When you're writing these, you really should be doing the 4-step process and writing out all 4 pieces of that. Here's the state, here's the plan, here's the do, recording the data, and here's the conclude. All 4 of those things should be written down. So here is a summary, pause, read, make sure these things make sense, and then off you go to more practice problems.